Hello everyone, I am Dr. Mahima Rabari, ANRF and PDF at the School of Chemical Sciences, IIT Mandi. Today my presentation will focus on visible light responsive photoswitches and liquid crystals from fundamental concept to molecular solar thermal energy storage applications. Stimuli-responsive materials. Stimuli-responsive materials are the materials that can change their physical or chemical properties when exposed to an external stimuli. These stimuli may be physical, such as temperature, electricity, etc., and chemicals such as pH or redox condition, or biological, including enzymes or biomolecules. Due to these unique properties, smart materials find application in drug delivery, actuators, sensors, environmental remediation, and energy storage. Among all the stimuli, light is particularly attractive. This naturally brings us to the question, why should we specifically use light? So, light is one of the cleanest and most precisely controlled external stimuli. Unlike heat or chemicals, light can be switched on and off instantly, directed to a specific location, precisely controlled through its wavelength, intensity, direction, and polarization. As we all know, sunlight is an abundant and renewable energy source. Instead of directly converting sunlight into electricity, and another attractive strategy is to store solar energy directly within the molecule as chemical energy. And this concept forms the basis of molecular solar thermal energy storage, commonly known as MOS. Global energy demand continues to increase, while the excessive use of fossil fuel contributes significantly to the climate change, and therefore the renewable energy technologies are becoming increasingly important. The abundance of sunlight makes solar energy harvesting and storage is one of the most promising sustainable solutions for the future. However, solar energy is intermittent because sunlight is only available during the daytime, and this creates a need for the efficient energy storage technologies. The key component of the most technology is the molecular photoswitches. Here are some examples of the molecular photoswitches known. Molecular photoswitches exist in two interconvertible forms, low energy stable isomer and the high energy metastable isomer. Upon absorbing the light of suitable wavelength, the molecule undergo reversible photoisomerization, and during the structural transformation, solar energy is stored within the metastable isomers. Later, the molecule returns to its original stable form, and either thermally or by irradiation with another wavelength, releasing the stored energy as a heat. And this reversible process can be repeated over many cycles without degrading the molecules. Most systems address the challenge of solar energy storage by storing solar energy directly within the chemical bonds. Unlike the batteries, this system requires no electrical conversion and can store energy for the extended period before releasing it as heat wherever required. Over the past decades, several class of the molecular photoswitches have been investigated for most application. Examples include azobenzene non-bondadines, dihydroazolenes, valvoline, diruthenium complexes, and many others. Each system offers certain advantages but also suffers from the specific limitations. Some possess a high energy storage density but absorb only UV light, while others exhibit poor thermal stability or limited cycling performances. Therefore, developing the new visible light responsive photoswitches remain an important research directions. Another focus of our interest is the liquid crystals. Liquid crystals are the unique state of matter that possess the fluidity of liquids while maintaining the certain degree of molecular order like crystals. They are mainly classified into thermotropic and lyotropic liquid crystals. Thermotropic liquid crystals phase behavior is controlled by temperature, and in the lyotropic, the self-assembled structures such as micelles in the presence of solvent. Depending on the molecular shape like rod, disc, band core, or chiral, they are organized into different mesophases like nematic, smectic, cholesteric, or columnar. Now, their self-organizing property making them ideal for a wide range of advanced functional materials. Liquid crystals respond efficiently to external stimuli such as light, temperature, electrical field, etc. And they are already widely used in the display technologies and now emerging as a promising functional material for advanced applications. Liquid crystal possess several characteristics that make them ideal for smart materials. Their self-assembly into highly ordered structure exhibit tunable optical properties, undergo reversible switching, and can easily realign under external stimuli. These unique features make liquid crystals highly attractive candidate for the integration with the molecular photoswitches. Now, Here, this slide summarizes the central idea of our research here. So molecular photoswitches alone can store solar energy, but they function as isolated molecules, whereas liquid crystal in contrast provide an ordered and adaptive molecular environment. By combining these two systems, we can improve molecular alignment, enhance photoisomerization efficiency, increase energy storage density, and stabilize metastable state and achieve controlled heat release. And this integration also facilitates the fabrication of practical smart materials and devices. So therefore, liquid crystalline photoswitches represents a highly promising platform for the most systems. Several research groups have already demonstrated the LC photoswitches that retain both efficient photoisomerization and liquid crystalline orders. These studies clearly established that integration of the photoswitches into LC system is feasible. However, a major limitation of this reported system is that they primarily rely on the UV light for the photoswitching and energy storage. Since UV light represents only a small fraction of the solar spectrum and may cause photodegradation, it limits their practical applicability. Furthermore, the number of visible light responsive LC MOS system remains very limited, and this research gap forms the primary motivation of my current work. So why visible light? Because it constitutes nearly half of the solar spectrum. Photoswitches that operate under visible light can utilize sunlight more efficiently than the UV responsive system. Visible light is also safer and cause less photodegradation and is compatible with the low power LEDs as well as natural sunlight. And ultimately, our goal is to develop highly efficient, reversible, sustainable, and practical photoswitches capable of operating under visible light for most application. So this work begins with the selective, suitable, visible light responsive photoswitch scaffolds. This molecule will be chemically modified, and this molecule to exhibit interesting LC behavior. After synthesis, the characterization will be done with general spectroscopic technique. Photophysical studies will be carried out via UV visible spectroscopy, and for further photoisomerization experiments, and thermal properties will be investigated using DSC and TGA, and mesomorphic behavior will be studied using POM-XRD, and finally the most performance of this material will be evaluated to establish structure property relationship and develop prototype for the smart energy materials. So our group, my mentor Dr. Indu Bala, research group at the School of Chemical Sciences, IIT Mandi. Our research group mainly focus on the molecular materials, supramolecular chemistry, liquid crystalline materials, photoresponsive system, and sustainable energy materials. And here is our beautiful campus of IIT Mandi. And I would like to acknowledge ANRF for the financial support, my mentor for her invaluable guidance, and School of Chemical Sciences, IIT Mandi, and Dean Shrik and Shrik Office for their administrative support and for ensuring smooth execution of this project. Thank you very much.